Hello, so this is the starting of the part 3.2 of the seminar about the thermoeconomic functional analysis. We have first to complete the discussion about the notes of the theory of the exergetic cost. So far we have discussed the exergetic cost and unit exergetic cost of the exergy flow of a system. Now we move to what are called thermoeconomic costs, that are, I can say, the monetary evaluation of the exergy, of the value of the exergy flow flowing in a energy system. So if we consider not only the exergetic transformation, inside the system, so part of the exergy is destroyed in form of irreversibility, but we consider also the monetary value of this exergy flow and the monetary value of the component, so the cost of investment of the components which are used inside the system, we can write, as we wrote a balance in terms of exergetic cost, we can write a balance in terms of monetary cost. So if we consider also the monetary cost linked to the energy system, the monetary balance of a generic component can be written as follows. The term P Greek, which is called the thermoeconomic cost of the product Pi of a component I, is equal to the P Greek, so the thermoeconomic cost of the fuel of the component I, plus the investment, the recovered investment cost of the component I, which is called Zi. So the symbol P Greek represents the thermoeconomic cost of the exergy, fuel or product of the component I, while the term Z represents the cost linked to the investment and maintenance. Usually we add also the maintenance cost, we include also the maintenance cost of the considered component I. In this case, all the terms are expressed in terms of monetary flow. So they are expressed all in terms of monetary cost per unit time, so it means euro, for example, per second, or dollar per second. Again, it's easy to define the concept of normalized cost, so unit cost obtained dividing the thermoeconomic cost of exergy flow divided the exergy flow itself. This cost becomes now, in terms of name, becomes the unit thermoeconomic cost. So it is easy to define the concept of unit thermoeconomic cost of exergy flow as a ratio between the thermoeconomic cost, P Greek, and the exergy flow itself. So a unit thermoeconomic cost of a flow I, let's say, Ci, is equal to the thermoeconomic cost of the flow I divided the exergetic flow of the flow I. It is expressed in terms of monetary unit, let's say euro or dollar per kilojoule. So again, we can see that the balance in terms of thermoeconomic cost can be written in the following way after the introduction of the unit thermoeconomic cost. So the unit thermoeconomic cost of the product of the component I, CPI, multiplied by the exergy flow of the component of the product of the component I, so CPI, is equal to, again, the unit thermoeconomic cost of the fuel of the component I, CFI, multiplied by the exergy flow of the fuel of the component I, CFI, plus, remember, the recovering of the investment cost of the component I, which is called Zi. Putting all together, we obtain that the cost of the product of the component, the unit thermoeconomic cost of the product of the component I, is equal to the unit thermoeconomic cost of the fuel of the component I multiplied by a ratio Ki, which is, you see, the ratio between the exergy flow of the fuel divided the exergy flow of the product, plus this ratio between the recovered investment cost Zi of the component I divided the exergy flow of the product of the component I. Again, following the same approach used in the case of the exergetic cost that we have seen in the part 3.1, the term economic cost can be evaluated through a matrix equation which use the economic balance applied to every component of the plant. So we can have an equation of economic balance, so balance of the term economic cost, applied to every single component of the system. So the balance, you see in the way that we have written it, is equal to the sum over the mm flow of the parameter aij, with the same meaning of the parameter that we have already seen in the exergetic cost equation, of p Greek j, so the term economic cost of the flow belonging to the component belonging to the system. These are equal to minus, because of the balance, the z investment cost go to the other side of the equation, so minus the recovered investment cost of the component I. This is a balance equation of term economic cost that has to be written to all the n components of the system. You remember we can write it in a matrix form, which is again the same topological matrix A that we have already introduced in the exergetic cost theory, multiplied by the vector of the term economic cost of the exergy flow of the system, p Greek, equal to the vector of the negative minus the investment cost, the recovery of the investment cost, the cost of the component of the system, zi. Again, we have to close the equation, the system of equation. We have to add auxiliary equation in order to solve the system. The auxiliary equation in matrix form are written again as alpha by p Greek equal to omega z. So alpha is again the same matrix of the auxiliary equation that we have already written in the case of the exergetic cost calculation. The vector omega z is the vector of the external evaluation again, but in this case expressed in monetary terms. So the matrix alpha is the same introduced in the calculation of the exergetic cost. The vector of the no values omega z depends on the external economic evaluation of the inlet and outlet flow exchanged between the system and the external environment. Is again the same external evaluation that we have done in the exergetic cost, but in this case expressed in monetary form. So as an example, omega z, the vector, can be expressed as unit cost of the external fuel, let's say, which is the term C. Let's say the unit cost of the flow of natural gas injected into the system by the exergy flow of this flow of natural gas injected to the system. So the economic evaluation is related to the term C, which is the value which economy gives to this flow. So again, the complete matrix equation becomes again the same topological equation, matrix A over the equation, the matrix of the external evaluation alpha, multiplied by the vector of the term economic cost that has to be evaluated. This is equal to the vector of minus the investment cost of the components and over the vector of the external monetary evaluation of the external exergy flow. Again, the matrix alpha A over alpha is the same in case of calculation of the exergetic cost and of the term economic cost. So this matrix is topological, can be used both to calculate the exergetic cost and the term economic cost. So I can stop here this second part and moving now to the third part of this seminar.